Okay, welcome everybody. Today we're going to talk about lesson number 19. This is the final lesson before our next assessment, and it's on section 2.5, which is about zeros of polynomial functions. Just to make sure that it's clear, even though we did have in homework 18, we had no official lesson 18, so I just figured by naming this lesson 19, it would match up with tonight's homework 19, and that would just make things easier for everybody. So the first and most important thing we're going to talk about here in section 2.5 is something called the rational root theorem. As you can see from this snapshot from your book, it's also called the rational zero test. So again, just please make sure you know that those two things are equivalent. Here's what the rational root theorem says. If a polynomial f of x equals, and then you have that whole big fancy long notation there, just to kind of make sure you understand where these are coming from. If you start by looking at the variables, they're saying x to the n, which means you could have a polynomial of any degree. Then what they're saying is that the next term would be x to the 1 less, then the next term would be x to the 2 less, and then eventually you'd end up with x squared, x to the first, and then no x at all. And your coefficients would just be matching. So if this was x to the n, this coefficient would be called a sub n. That would be the leading coefficient. A sub n minus 1 would go to x to the n minus 1, and then on to the end, a2 would go with x squared, a1 would go with a to the x to the first, and then of course your final term here would have to be your constant with no variables. So basically, if you have a polynomial and it has integer coefficients, which for our purposes it always will, then every rational zero must take the form p over q. Pay special attention to the fact that it has to be a rational zero. That is all we can say for sure about it. So the rational zeros take the form p over q, where p and q have no common factors besides 1, and p is a factor of the constant term, a sub 0. So it's basically all the things that divide the last term, where q is a factor of the leading coefficient, which is all the things that would divide a sub n. So it probably is important that you write this down. So I'll kind of speak on it for a minute and then pause the video as needed. As we go through this video, there's a lot of, there's quite a bit of writing and there's quite a bit of discussion. So again, I will try to pause the video often so that you can keep up. Otherwise, remember, you can always go back and review and rewrite anything down that you might want to. So how are we going to use the rational root theorem, which again, I call the RRT for short? So let's say you had a problem that said, use the rational root theorem to find all the roots. So think about all the strategies you have right now for factoring and solving polynomials. This is not factorable. Grouping wouldn't work. No difference of squares, no difference of cubes. There's nothing that we currently know how to do that would factor and solve this polynomial. For the record, if there was some easier, better, more efficient method, you should certainly use it. But in a case like this, our only option is the rational root theorem. So the p's are going to be all the things that divide the constant, and the q's are going to be all the things that divide the leading coefficient, which in this case would be positive 1. As you make a list of all your p's and all your q's, don't forget positive and negative. Generally, you write positive or negative as plus or minus, and you go from the smallest to the largest. So all the things that divide 60 are plus or minus 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, 30, and 60. Those are all the things, positive and negative, that divide evenly into negative 60. Then your list of q's are all the things that divide evenly into positive 1, which would just be plus or minus 1. When your q is plus or minus 1, then when you go to make your list of x's and you do your p's over your q's, because of the fact that the q is just equal to plus or minus 1, that means that your list of x's just equals your list of your list of x's just equals your list of p's. So really, there's no need for me to write them again. How many possibilities is that? Remember that when you count them, you would count each number as 2 because it's plus or minus. So as I go from left to right, that would be 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24 possible rational roots based on applying the rational root theorem. So 24 possible rational roots, that sounds like a lot. How are we going to find them? How many can there be? How can we narrow the list down? Well, that's going to be the focus of this lesson. So this particular problem, we're actually going to talk about for the majority of the lesson. How are we actually going to solve this problem? But more importantly, how are we going to take those 24 possible rational roots and try to make some sense of them, as opposed to just trying to plug in 24 numbers? Because again, that's not very efficient. So first thing that you want to remember here is that these 24 values are only possible rational roots. So possible means they may or may not work, and rational meaning that there could still be imaginary or irrational answers out there. Unfortunately, the rational root theorem doesn't tell us anything about those. Here are some other things that we do know, though. At most, 4 of these rational roots will work. The reason being, this is a quartic, which means that at most, it could have 4 total solutions. And yes, we kind of know that with common sense, but in case you were wondering, the way we know that mathematically is that's called the fundamental theorem of algebra. At minimum, none of them could work, which means we could sit there and try 24 different possible rational roots and none of them could work. Again, for the record, I would never do that to you, but just make sure you know that there are only the possibilities. Best case scenario, we're able to find 2 of them that work because every time we do synthetic division, we're reducing the degree of the polynomial by 1. So if we find 1 root, that takes us from a quartic to a cubic. And then if we find a second one, that reduces us to a quadratic. And that's the dream, because obviously we know how to solve every quadratic. So then, in addition to just those kind of informational pieces, how do we then avoid testing 24 possible roots? Well, here are some tips. So the first bullet is you can generally eliminate your large numbers from your list unless there are large coefficients. One of the possible rational roots on our list was 60. In order for 60 to work, that would mean that x minus 60 was a factor of this polynomial. That doesn't really seem very logical, considering there would have to be 3 other factors. Think about, for 60 to work, you would have to do synthetic division. You would have to put 60 in the box. Seems like your numbers are going to get very large very quickly. So generally speaking, don't test the really big numbers unless you have really big coefficients. Second and third, again, a little bit of common sense. Let's say that the majority of your coefficients were mostly positive. A good strategy would then be to check the negative roots. Again, the only way you know that something is going to work is if it has a remainder of 0. So if you have mostly positive coefficients, try a negative answer. And if you have mostly negative coefficients, then try a positive answer. So again, kind of just common sense. In addition to that, if you had a graphing calculator, you could graph it and then look at the graph for the solutions. You would, of course, be looking for the zeros and the x-intercepts. Obviously, wherever the graph crosses the x-axis, that has to be one of the solutions. Again, that doesn't help us in terms of finding imaginary roots, but still something to keep in mind. And then finally, you can actually use the intermediate value theorem. And then remember, you look for a sign change. So let's say you were to find that f of 1 was negative 54, and then you were to find that f of 5 equals 350. The fact that there was a sign change from negative to a positive means that the graph had to cross the x-axis somewhere between 1 and 5. So there had to be an x-intercept there, which again, if I look at my entire list of roots, there's only a handful of them that are between 1 and 5. So that would help me whittle down my list significantly. There are yet a few more ways that you could take those 24 possibilities and kind of narrow them down into the ones that we know are going to work. So this is Descartes' rule of signs. Again, I'll tell you in the past that this is something that students often would forget on the test, but that shouldn't be an issue for any of you because of the fact that it's open notes. So again, start by looking at the qualifier. If you have that big fancy polynomial with real coefficients and the constant not equal to 0, again, I'm not really going to trick you and ever give you a polynomial that doesn't meet those requirements, but it's still important to know. And then there are 2 pieces of the rule, part 1 and part 2, and we're going to do each one. So part 1 of the rule says the number of positive real zeros of f is either equal to the number of variation in sign of f of x or less than that number by an even integer. So that is a real mouthful. I'm going to show it to you in practice, and it's actually much easier in practice than it is to read. But again, this tells you only about the positive real zeros. So while it is an efficient way of narrowing down your choices, it is very specific. So notice that I recopied my polynomial here, but notice that I put a positive in front of the x to the fourth, just to remind myself that it is in fact positive. What you're going to do to use part one of this rule is you are going to count the sign changes. So anytime there's a change from a positive to a negative or a negative to a positive, that counts as a sign change. So starting with positive x to the fourth, as I go from positive x to the fourth to negative 3x cubed, that counts as a sign change. Then as I go from the negative 3x cubed to the positive 6x squared, that counts as a second sign change. When I go from positive 6x squared to positive 2x, that is not a sign change. And finally, when I go from positive 2x to negative 60, that's a third sign change. So in total, there are 3 sign changes. And according to this rule number 1, it says that the number of positive real zeros of f is either equal to the number of variations in sign, so 3, or less than that by an even integer. So if you were to go less than 3 by an even integer, you'd have to subtract 2, which means that there are 3 or 1 positive real zeros. So that's the first conclusion that you can draw based on part 1 of Descartes' rule of signs. You count the sign changes, and then it's either that number or less than that by an even degree. So if there were 5 sign changes, it would be 5 or 3 or 1. If there were 2 sign changes, it would be 2 or 0. So less than that by an even degree means you can only decrease by 2s. So that's part 1 of Descartes' rule of signs. There are 3 or 1 positive real zeros. And now we're going to go ahead and talk about the number of negative real zeros. So this is part 2. So if you want to find the negative real zeros, it's equal to the number of variations in the sign of f of negative x, or less than that by an even integer. So first off, I have my regular f of x. In order to employ part 2 of this rule, I have to find f of negative x. So that means that everywhere there's an x, I have to go ahead and change it to a negative x. Then I have to go ahead and actually do the calculations. So when I do negative x to the fourth, that turns back positive. Negative 3 times negative x cubed, that would change to a positive 3x cubed. Then when I square it, I get a positive 6x squared, followed by a negative 2x, followed by a negative 60. So now that I have calculated f of negative x, I'm going to go ahead and count the sign changes. So from a positive to a positive, nope, nope, there's 1, and that's it. So the fact that there is only 1 sign change means that there has to be 1 negative real solution. And that actually is a good piece of information because there's only 1 negative real solution, which means if I find a negative rational root, that has to be the only one, and then I no longer have to test any of the negatives. All right, so back to our actual problem here. Now, here's the thing. You'd be surprised how good you actually get at picking a value that works the more you do of these. Frankly, after doing this for 16 years, I'm really good at picking the answer. And my goal is never, not now in the lesson or on a test, to have you sit there and just test. That would be silly. So again, looking at this problem, remember that we had 24 possible solutions. We kind of already said the fact that we're not going to include the large number. So we're not really going to include 15 or 20 or 30 or 60. We know that there is exactly 1 negative real solution. So I'm going to go ahead and look for that one. So I'm going to copy my coefficients, 1, negative 3, 6, 2, and negative 60. And then here's the thing, because I made this problem, I happen to know that -2 works. So if you were on your own, my advice is, unless you have a gut feeling about one of the answers, just test them in order from smallest to largest. So you would test 1, you would test -1, you would test 2 and -2. And the truth is, you'll be able to tell relatively quickly whether or not a solution works. And again, you'd be surprised at how good you get at picking the right answer after you do a bunch of these. So how do I know that it works? Well, bring down the 1 times -2, add the column, multiply to the box, add the column, multiply to the box, positive 60, and look at that. I've got a winner. Make sure, of course, that when you're doing synthetic division, you would, of course, use 0 placeholders if and when they were needed, although in this place, we're good to go. So at this point, if I was on my own, the fact that I found a negative answer means I would not test any other negative possibilities, because there's only one negative answer and I found it. If I'm going to try to get this down to a quadratic, I have to look for a second answer. And again, because of the fact that I made this problem, I happen to know that 3 works. So bring down the 1, 3, -2, -6, 10, 30, and 0. So that's the dream. I happen to find 2 solutions, which now brings me down to a quadratic. So remember that that 1 represents x squared minus 2x plus 10. If that was factorable, there'd be 2 factors of 10 that add up to be -2, which I know is not the case. So in order to solve for those x's, I'm going to have to set this equal to 0 and use the quadratic formula, which I'm going to go ahead and do on the next slide. So to use the quadratic formula, x equals -b plus or minus the square root of b squared minus 4ac all over 2a. Underneath the radical, that's 4 minus 40, which is -36. The square root of -36 is, of course, 6i. And I can divide everything by 2, which means I get answers of 1 plus or minus 3i. Remember, technically, there are 2 answers there, a pair of conjugates, as it were, 1 plus 3i and 1 minus 3i. So you are trying to find 4 solutions, and you are trying to find 4 factors. So just to be clear, the 4 solutions to this problem are the -2 and the 3 that I found by testing my synthetic division, and then 1 plus 3i and 1 minus 3i. And yes, you can write them as plus or minus, but I'm just going to write them out to make sure we know that there are 1, 2, 3, 4. And again, remember, when it comes to imaginary and irrational solutions, they have to come in pairs, conjugates only. So then what would the factorization look like? Well, again, it would depend on how far I told you to factor. So if I told you to just factor over the real numbers, the -2 would be x plus 2. The positive 3 would be x minus 3. And then x squared minus 2x. Eraser, sorry. There you go. Back to my pen. So x squared minus 2x plus 10. If I told you to factor it just over the real numbers, then that would be as far as I could go. If I told you to factor completely, this would be x plus 2, x minus 3, and then x minus one of the roots, which would be 1 plus 3i. And then x minus 1 minus 3i. Now, that looks kind of gross. I don't actually ask you to do that all that often, but I could. So again, just to clarify, in this first bullet here, that would be what would happen if I told you to just factor so that it was irreducible over the real numbers. Then if I told you to factor completely, that would mean I would want the complex numbers as well. So x minus 2 or x plus 2, x minus 3. Then it would be x minus one of the roots, x minus the second root. Know that if you wanted to, you could distribute that minus to each of those parentheses, although not required. So I believe that it said find all 4 factors and find all 4 solutions, which I technically did. And then I don't know that it asked me to do it, but I am going to go ahead and graph this. So if I'm going to graph this, the only x's that I have, again, are -2 and +3 in terms of being real. And those both have a multiplicity of 1. The y-intercept would be 0, -60. And because of the fact that this was positive x to the 4th, my end behavior would be up, up. So here at -2, 0, here at 3, 0, and down here at -60. If the end behavior is up, up, I would cross through the multiplicity down to the y-intercept, and then eventually come back up through x equals 3. So you can see here, it actually kind of looks like a quadratic, but that's because there were 2 imaginary solutions. Remember, we call this right here a turning point. The maximum number of turning points is 1 less than the degree, but there can be fewer. And the fact that this is a quartic that looks like a quadratic is because of the fact that I had those imaginary solutions. So of course, on a test or quiz, you're not going to have one big problem like this because that would be very hard to grade, but it is a good technique in terms of a lesson. And then I have just one more problem here just to make sure you understand the specifics. So here's this cubic polynomial. List all the possible rational roots. Use Descartes' rule of signs to determine the number of positive and negative solutions, real zeros rather, and then find all the solutions and factor completely. So again, P's in the back, Q's in the front. All the things that go into -2 are plus or minus 1 and 2. All the things that go into 6 are plus or minus 1, 2, 3, and 6. Now you have to make a list of all the x's, which means you have to put all your p's over all your q's, and you have to reduce them. If you go to do p over q and it gives you something that's already on the list, then you don't write it a second time. So I'm going to start by putting plus or minus 1 over all the plus or minus q's. So that's going to give me plus or minus 1, 1/2, 1/3, and 1/6. Then I'm going to do my other p, which is 2 over all my q's. So that's going to give me plus or minus 2 over 1, which is new. 2 over 2 is 1, which I already have. 2 over 3, which is new. And then 2 over 6 becomes 1/3, so I'm not going to write that a second time. So if you count those up, plus or minus, that's 2, 4, 6, 8, 10, 12 possible rational roots. Again, at most, 3 of them could work. At minimum, none of them could work. Because this is a cubic, if I was to find just one that worked, I would be able to get down to a quadratic, which would make this a very simple problem. So just to go ahead and see how the Descartes rule of signs helps us. So again, I recopied for you the rule, and we're going to go ahead and start with condition number 1. So I'm going to count the number of sign changes. 1, 2, 3. So the fact that there are 3 sign changes tells me that there are going to be 3 or 1 positive real zeros. Remember, it's either the number of sign changes or less than that by an even integer. So there's either 3 or 1 positive real zeros. Now to employ the second rule, everywhere there's an x, put a negative x. Then do the calculations. Excuse me. Count the sign changes. Nope, nope, nope. So the fact that there are no sign changes means that I can say for a fact that there are 0 negative real zeros. So there are no negative real solutions to this problem, which means of my list, which has 12 possibilities, plus or minus, I could eliminate all the negative possibilities because Descartes' rule of signs tells me that those don't work. And obviously going less than that by an even degree, you can't have a negative number of solutions, so that wouldn't be a thing. Just to go ahead and follow the problem all the way through and finish it off. So 6, -4, 3, and -2. None of the negatives work, and it turns out that actually none of the integers work, and I'm going to have to choose a fraction in order to get it to work. So bring down the 6, multiply to the box. That would give me 12/3, which would be 4. 0, 0, 3, 2, and 0. Because I found an answer, that would be 6x squared plus 3. I could then factor out a 3, which would give me 2x squared plus 1. Remember that having that extra 3, that's because of the fact that, I would technically write that 2/3 as x minus 2/3, but because of that extra 3, I could multiply each of them by 3, which is how I would get 3x minus 2. So 3x minus 2 times 2x squared plus 1, that would be my factorization. Then if I actually want to go ahead and solve, I guess I thought I had more room. I'm going to have to take that 2x squared plus 1, and I'm going to have to go ahead and set it equal to 0. So if I set it equal to 0, I would subtract the 1 and divide by 2, which means that x squared would equal negative 1/2. Take the square root of both sides. You're going to get x equals plus or minus the square root of negative 1/2. I'll just go ahead and finish it up on the homework screen. So the square root of negative 1/2, that would be equal to plus or minus I over the square root of 2. You would then rationalize, which would be plus or minus I radical 2 over 2. So again, just to clarify from the previous problems, my 3 solutions are plus or minus I radical 2 over 2 and 2/3. My factorization, if I said do it over the real numbers, would be 3x minus 2 times 2x squared plus 1. And if I asked you to factor it completely, it would be 3x minus 2 times x minus I radical 2 over 2 times x plus I radical 2 over 2. So look at that. That brings us to homework number 19. So this is section 2.5, and it's the following problems. Again, some of them, not all of them, say actually solve using the rational root theorem. So when it does say solve using the rational root theorem or the rational zero test, make your list of p's, make your list of q's, make your list of p over q's, and then go ahead and ultimately find the ones that work. So thanks very much for tuning in, guys, and we will catch you next time.